Yay, we know how to connect the graph of a quadratic function to its algebraic form, right? We know how to find the vertex from the, ax squared plus bx plus c, and axis of symmetry, all that good stuff, okay? Now we ask the question, is there another way to do this? Yeah, with transformations. In fact, when we were looking at our parent or our base functions back when we were studying transformations, that included the graph of a quadratic function, so x squared, right? And so we know that that was our base function. And so the transformation model, we know there's the A, B, C, D, and we would do it in the order of CBAD, right? C and then B and then A and then D. And so if we work with the quadratic function and just kind of insert this all in, we get the general function as A parentheses bx minus c quantity squared all plus D. Okay. However, we make a simplification. Okay. If we're working with a quadratic function, that b that's inside on the x, we can actually factor that out and it can be a part of a. So we generally, when we work with the transformation of the quadratic function, the base one, that is, we typically don't have a b, so it'd be SAD, C-A-D, would be the order of transformation in this case. Okay, so it makes our life a little bit easier because we don't have to deal with that horizontal scaling. And again, A, C, and D all still serve their general roles of A being the vertical scale, C being the horizontal shift, and D being the vertical shift. Okay, so let's look at this in Desmos. Okay, so I have that general model in. Okay, I've made sliders for A, C, and D. Okay, and in the graph of the quadratic function, we can now say, okay, this general one, okay, C and D are 0, so this would just be y equals x squared. And we see the vertex is at 0, 0, and we have axis of symmetry along the line x is equal to 0. Okay, fine. And then we know A is positive, so it's concave up, and therefore when it's concave up, we have a minimum occurring in our graph. Okay, fine. Let's change some of these values. So let's change C, I don't know, just a little bit. Let's change it to 5, okay? We see that the vertex shifted to the right 5, okay? And so this would be x minus 5, okay? And the x coordinate of our vertex is still 0, okay? So the vertex is at 5, 0. C is 5, D is 0. If D changes to, I don't know, let's move it down to minus 2. Now the vertex is at 5, comma, minus 2, right? And that happens to be values of C and D. Oh, okay. So like in this form, in this transformation form, we actually can find the vertex quite easily. It's just so C would be the X value of the vertex and D would be the Y value of the vertex. Oh, that's kind of nice. And then if we wanted to make the axis of symmetry appear, I can just add the line X equals C, okay? And there we go. And maybe after we add that, we want to, modify it just a little bit, maybe make it a dashed line. And I always did it in orange, but that's really hard to see. Let's do it in blue. Okay, so then we see the axis of symmetry going right through that vertex as well. Okay, so the upshot of all this is that in this transformation model, okay, we can actually find the vertex quite easily. Okay, C is the x coordinate of the vertex, D is the y coordinate of the vertex, and we know the axis of symmetry. So this general, this form that we get from transformations is actually so important it has its own name. We call it the standard form of a quadratic function. Okay, I don't know why some books call it standard form. Sometimes you see it as vertex form, tomato, tomato, really. And the only other thing that changes when we use this definition is we talk about H and K as being, instead of C and D, as being the location of the vertex. So if we have X minus H, square all squared plus K, in that form, HK is a vertex. And then we have our axis of symmetry is just line X is equal to H, okay? And then concavity was still determined by the sign of A. So there we go. We have another bit of language to use around quadratic functions, but this form is actually pretty helpful. Okay, it allows us to perhaps sketch a graph of the function maybe quicker or more easily. Let's see it in action. All right, so we're given a quadratic function and it says label all important aspects. Okay, so I'm just going to come over here, get my graph set up. Okay, so I'm just going to start kind of labeling what I know. Okay, it is in standard form, so I can say that one bit of information, the vertex, is at this is H and this is K. So the vertex is at 2, 1. Okay. I know the axis of symmetry is at the line x is equal to 2. Okay, so I'm just going to start labeling this information on here. So I have my axis of symmetry. On my vertex, 1 right there. And I'll label that on here just because this isn't to scale exactly. Okay. Let's see. So that's really all that oh, actually, I can get one more thing. Okay. I can say that A, this value out here, is the value of A. A is equal to -1, which is less than 0. So it's concave down, and it has a max. It has a maximum. Okay. So that's really all I can tell easily from this. The other things that I typically like to plot are the zeros, and the y-intercept. Okay. And for each of these, I'm just going to say, let's go through and do the math. So zeros, I would, set y equal to 0 and solve for x. Okay. If I do that, I would have 0 is equal to negative x minus 2 squared plus 1. Okay. And then I just need to solve for x. Okay. So subtract 1, -1 is equal to negative x minus 2 quantity squared. Divide both sides by a -1, which would make both sides positive. Okay. And so I have 1 is equal to x minus 2 quantity squared. I can solve this by square rooting both sides. Okay, when I square root both sides, I have to remember the plus and minus. Okay, so what I did next was I introduced a square root. Okay, and so then I get x minus 2 is equal to those. So I'm going to split this into two equations. X minus 2 is equal to positive 1, and x minus 2 is equal to -1. Okay, and solve for x. In this case, I get x is equal to 3, and x is equal to positive 1. Okay, so that means I have the point 3, 0, and 1, 0. Okay, oh, that's kind of nice. Right there, and that's a little far off. Right there. Okay. And for as far as the y-intercept, that's when x is equal to 0. So I'm just going to, again, number crunch. So f of x is equal to negative 0 minus 2 quantity squared plus 1. And going through the arithmetic, so this would be -2 all squared is positive 4. But then I have a negative on that, so it's -4 plus 1 gives me a -3. Okay, so I get something like that. And by symmetry, I'd have a point down here. Okay, and in all, I get my graph of my parabola. Okay, and I'm just going to label these as 3, 0, 1, 0, 0 minus 3, and I'm going to label this as 4. Let's see, yeah, that's a distance of 2, so it'd be 4 over here because it's 2 away, and then -3. Okay, and there I go. I have my graph of my parabola. So you can still use this. You can use this as a different way to get the graph of a parabola. Okay. The last thing that we need to be sure is that yes, we have kind of our expanded form or our general form, the ax squared plus bx plus c, and then we have standard, which is this form where you can find the vertex easily. You have to be able to go through them, go from one to the other as needed. Okay, so to go from standard to general, okay, so from that vertex form over to general, just FOIL it out. Okay, so again, you'd have to do like x minus h times x minus h. Okay, multiply that times a and add k. Okay, so do the arithmetic and do what you do, or do what you need to do. But for going from general to standard, that's a little bit more difficult. Technically, you would need to complete the square, but maybe the easier way is, since h and k represent the x coordinate of or the x and y coordinate of the vertex respectively, just find the vertex and then put the numbers in. Okay, and pick off a. That's an easier task. Okay, so an example of that is in this one. If we want to write it in standard form, okay, so we would need to say, okay, in this case, a is 2, okay, and then to find h is the x coordinate of the vertex, which is negative b over 2a, and in this case, it would be negative of a negative 6 all over 2 times 2. Okay, so positive 6 over 4 gives me 3 over 2. Okay, and then for k is just going to be whatever I get once I put 3 over 2 into the function. Okay, so I can say this is 2 times 3 over 2 squared minus 6 times 3 over 2, and then all plus 8, which gives me 7/2. Okay, so then that means all of this information I can assemble together and just say that the standard form, or I should actually use the function name f of x is equal to, okay, it would be a x minus h quantity squared plus k. And in this case, we know that a is 2, and then h is 3/2, and then k is 7 over 2. Okay, and that would be a nice easy way to represent the function that's given to us in general form as standard form. Okay, and we're done. Okay, so standard form, super helpful to find the vertex and axis of symmetry. And so make sure to be on the lookout for that form to help you graph a quadratic function more easily.